Ever feel like you're spending more time telling your computer asterisk how asterisk to do something, rather than just telling it asterisk what asterisk you want? You're not alone. We spend countless hours writing step-by-step instructions, meticulously planning every loop, every conditional, every single move. This is the world of imperative programming, the paradigm most of us know. But what if there was a different way? A way to simply describe the problem, lay out the rules, and let the computer figure out the how on its own. Welcome to the fascinating world of logic programming. Imagine you're trying to solve a Sudoku puzzle. With a language like Python or Java, you'd probably start by writing nested loops to iterate through each cell. You'd write functions to check if a number is valid in a row, a column, and a 3x3 box. You'd implement some form of backtracking to try different numbers and undo them if they lead to a dead end. It's a lot of procedural logic. You are the architect of the entire solution process. Now, let's look at this from a logic programming perspective, using a language like Prolog. Instead of writing step-by-step instructions, you'd simply describe what a solved Sudoku puzzle asterisk is asterisk. You would define the rules. A solved grid is a 9x9 matrix where every cell contains a number from 1 to 9. You destate the constraints. Every number in a row must be unique. Every number in a column must be unique, and every number in each 3x3 subgrid must be unique. You'd provide the initial puzzle with its given numbers. And that's it. You've described the problem, the conditions for a solution. Then you just ask the system, find a grid that satisfies all these rules. The logic programming engine takes your description and automatically searches for a solution that fits. It handles the searching, the checking, the backtracking, all the procedural heavy lifting behind the scenes. You focus on the asterisk, what asterisk. The machine handles the asterisk, how asterisk. This is the essence of declarative programming, and logic programming is its purest form. So, how does this magic actually work? It's all based on formal logic, the kind you might have touched on in a philosophy or math class. Logic programming languages use a system of facts and rules to represent knowledge about a particular problem domain. Facts are simple, unconditional statements of truth. For example, we could state, Socrates is human. In Prolog, this might look like human Socrates, a simple fact. We can add more facts. Human Plato, human Aristotle. Rules, on the other hand, are conditional statements. They define relationships and allow the system to infer new facts. A classic example is, if X is human, then X is mortal. In Prolog, this rule would be written as mortal X, human X. The symbol can be read as if. The X is a variable. This rule tells the system that, for any X, if you can prove that human X is true, then you can conclude that mortal X is also true. Now, with these facts and rules loaded into our knowledge base, we can ask questions or queries. We could ask, is Socrates mortal? We'd type mortal Socrates. The system would first look for a direct fact, mortal Socrates. It won't find one. But it won't give up. It will then look for a rule that could help it prove mortal Socrates. It finds our rule, mortal X, human X. We can also ask more open-ended questions. What if we query who is mortal? By typing mortal X, the system will again use the rule. Its goal is to find a value for X that makes mortal X true. To do this, it needs to satisfy the condition human X. It searches its facts and finds human Socrates. So, it sets X equals Socrates, successfully proves the rule, and presents Socrates as the first answer. But it doesn't stop there. It knows there might be more solutions. It backtracks, unsets the value of X, and continues searching from where it left off. It finds human Plato, so it presents Plato as the next answer. It does this again and finds Aristotle. After that, it finds no more facts about humans and concludes its search. It has automatically found all possible solutions based on the knowledge we gave it. This process of matching, substitution, and backtracking is called unification and resolution, and it's the core inference engine of logic programming. You don't have to code it yourself. This declarative style of problem solving has incredible advantages in certain domains. Think about artificial intelligence, building an expert system. For instance, you can encode the knowledge of a doctor or an engineer as a set of facts and rules. Then, users can query the system for diagnoses or solutions. And the system uses its logical inference to provide answers, even explaining its reasoning by showing the rules it used. Natural language processing is another huge area. Understanding the grammar and structure of human language is all about rules. A sentence is composed of a noun phrase and a verb phrase. A noun phrase can be a determiner followed by a noun. These grammatical structures can be expressed beautifully as logic rules, allowing a program to parse sentences and understand their meaning. Database. Querying is also inherently declarative. When you write an SQL query, like select name from users, where country equals Canada, you're not telling the database asterisk how asterisk to find the data. You're not specifying which index to use or what join algorithm to perform. You're simply asterisk describing asterisk the data you want. The Database Management Systems Query Optimizer, a highly complex piece of software, figures out the most efficient way to retrieve it. This philosophy is identical to logic programming. In fact, Datalog, a subset of Prolog, is a powerful database query language. Logic programming is also a fantastic tool for solving complex scheduling and optimization problems. Imagine trying to create a university timetable. You have hundreds of courses, dozens of rooms, thousands of students, and a mountain of constraints. No student can be in two places at once. A professor can't teach two classes at the same time. A room can't be over capacity. Certain courses need specific equipment, and so on. Trying to write an imperative algorithm to solve this would be a nightmare. The number of possibilities is astronomical. But with logic programming, you just state all the constraints as rules. You provide the facts, the list of students, professors, courses, and rooms. Then you ask the system to find a valid timetable that satisfies all the rules. The built-in search engine will crunch through the possibilities and, if one exists, present you with a valid schedule. It transforms a horrifically complex coding task into a task of clear, logical description. Of course, logic programming isn't a silver bullet for every problem. For tasks that are inherently procedural, like rendering graphics or performing heavy numerical computations, imperative languages are often more direct and efficient. The thinking that a logic programming engine does behind the scenes, the searching and backtracking, comes with a performance overhead. Sometimes you really do need to control the how down to the last detail for maximum performance. Debugging can also be a bit different. Instead of stepping through code line by line, you're often tracing the logic of the inference engine, figuring out why a certain goal succeeded or failed. But the real power of logic programming is that it changes the way you think about problems. It forces you to step back from the low-level mechanics and focus on the high-level logic and structure of the problem itself. This skill, the ability to formalize a problem in terms of its essential rules and constraints, is incredibly valuable for any developer, regardless of the language they use day to day.